Hello, and welcome virtually to Brookhaven National Laboratory. I'm Bob Gordon, and I manage the U.S. Department of Energy's office here at BNL. Before you begin exploring this amazing place, let me tell you about the Department of Energy, Brookhaven's owner. The Department of Energy's Office of Science provides most of the lab's $700 million annual budget. We've hired Brookhaven Science Associates, a partnership between Stony Brook University and Battelle Memorial Institute, to run our laboratory, and especially the conduct of world-class science. You probably didn't know that the Office of Science is a world-leading supporter of research in the fundamental sciences. Battelle and Stony Brook are both leaders in science, education, and research. Together, we strive to realize the DOE mission to ensure security and prosperity through transformative science and technology solutions. And you're part of it. Welcome to BNL's Summer Sundays and enjoy the visit.
Hi, welcome to the Brookhaven National Lab Virtual Summer Sunday at the Center for Functional Nanomaterials, or CFN for short. My name is Priscilla Antunes. I am the Assistant Director for Strategic Partnerships at CFN, and my job is to help researchers from anywhere in the world explore using our state-of-the-art instruments and work with our expert scientists at CFN.
My name is Trishelle Copeland-Johnson. I'm the current chair for the CFN User Executive Committee. And I want to thank everyone for joining us today. Today, we're going to have a short virtual tour talking to some of our fellow scientists at the CFN and learning more about what they do. But before we start that, I want to give everyone a reminder that if you have any questions whatsoever throughout the discussion, please enter them in the respective chat for the virtual platform you are viewing us on, and we will do our best to answer them. With that said, I'm going to turn it back over to Priscilla to introduce the CFN.
Thank you, Trishelle, for moderating this event with me today. I am very excited that our audience gets to learn more about CFN and for them to meet a few of our scientists. Before CFN, I worked at Argonne National Lab and did my postdoc at IBM, and I was always fascinated with the research and the large collaborations that CFN has with universities, other national labs, industry, startups. And I think one of the most inspiring things about the scientists at CFN is how they also get to work with students, postdocs, early career researchers, and just train them and their students to use the instruments at CFN and really help them propel their research. So you get the sense that a lot of things go on at CFN, much more and beyond just research with nanomaterials and their devices. You'd be absolutely correct. This is a great group of people. These are one of my 4 favorite researchers, and they can tell you more about their experience working at CFN, but they'll definitely tell you more about their instruments and actually how they use to do their own research 50% of the time and help others with their own research the other 50%. So it's incredible to me to see them at work and then to come on Sundays and be here with you all to answer questions. So I'm obviously a fan. And a quick refresher, we design, make, and study materials and processes at the nanoscale. And at this ultra small scale, objects span only billions of a meter or just 10 to the negative 9 of a meter. So of course, we have Nano Day to remind us all that every year that 10 to the negative 9 is the scale size. So I will share the link to the site on the chats for those that I would like to get ready for October 9th. And finally, I'll leave you with my favorite example of to help others get a sense of the nanoscale, which is that you can fit up to 100,000 nanoparticles in the width of one human hair. I like this example both because we all have a good sense of what human hair is, and also because that's the example I used in my first presentation, my first research presentation, at a conference for the American Chemical Society. So thank you again for joining us today. And let's meet the panel, Trishelle.
Awesome. So we're going to get started introducing each of our esteemed panelists today. They're going to introduce themselves and share something surprising or interesting about themselves. So our first individual up is Aaron Stein, who leads the CFN nanofabrication facility. So Aaron, the floor is yours.
I'm muted. Hopefully I won't do that again. Hi, everyone. My name is Aaron Stein. As they said, I work in the nanofabrication facility. I got my PhD at Stony Brook, and I've been at the CFN ever since. I've been there for 18 years. And in fact, I was the first person hired to work at CFN. So I've been working there for a long time. I've got to see a lot of amazing science and a lot of amazing researchers come through. So I'm excited to talk to you about the work we do here.
Awesome. Thanks, Aaron. Next up, we have Suyun. Suyun is a material scientist in the CFN electron microscopy group. Suyun, what else would you like to share about yourself?
Hi, hello everyone. I'm Suyun, and I come from Korea. I did all my training in Korea, but also CFN gave me a lot of opportunity as a user, and I got nice training during my postdoc period, and also now I'm a staff scientist, and I'm operating transmission electron microscopes to study various nanomaterials. I'm happy to meet you and happy to share about the electron microscopy with you today. Thank you.
Thank you, Suyun. Next up is Gregory.
Something fun, Greg, that we don't know about you.
Okay, so something just cut out for a second, but I think everything's okay. Yes, hi, I'm Gregory Dirk. I got my PhD at the University of California at Berkeley, and after spending some time on the West Coast working at IBM and at a hard disk drive manufacturer, I jumped at the opportunity to come work at the CFN and explore some really kind of amazing research. I work in nanofabrication, doing things alongside Aaron, but I work in areas like where we call self-assembly. And you'll learn a little bit about that when Aaron presents his video. Fun fact about myself is I'm not going to brag about my athletic prowess, but I've done a few triathlons, and as a result, I've swum 2 times in the Hudson River. So.
Awesome. Thanks, Greg. Last but not least is Percy. Percy is a scientist in the CFN Interface Science and Catalysis Group. Percy, please tell us a little bit more about yourself.
Yeah, my name is Percy Zahl, and I did my PhD in Germany, in Hanover, before I proceeded actually already my first time to the US in Colorado and did another PhD there in Golden. Before I went actually back to IBM Zurich in Switzerland and did another PhD where I actually got kind of fascinated. I was always fascinated by scanning probe microscopy, but in particular there, I got really into the early stages, even before it worked, of these extreme microscopy, what I'm operating now. And I made myself envision, or actually a mission somehow, to develop this method further to the edge or cutting edge and keep working on it and provide it actually worldwide to our user facility, or to via our user facility to the users, the expertise, and even with being open to try and explore new things never been done. And yeah, it's just fascinating and to look at that magic world of atoms at the length scale, pretty much at the limit what you can see in real space. And yeah, I'm happy to share some details and answer all your questions about that later.
Awesome. Thank you, Percy. So we're going to get started with some introductory videos. First from Aaron. He's going to be discussing more about where materials like solar cells are made in his nanofabrication facility.
Hello, my name is Aaron Stein, and I'm standing here in front of the clean room, our nanofabrication facility here at the CFN. We use the instruments here inside the laboratory to create nanostructures in different materials. These structures can be used to change the properties of the material, whether it be the electric properties, how electricity flows through them, how the materials interact with light, or even how they interact with fluids or inside the human body. There are two different ways that we do nanofabrication, as it's called. There's top-down, where we kind of come down and control the designs and patterns that we want to make in the materials. And there's also bottom-up, where we let Mother Nature decide how the patterns are created in the materials. Here at the CFN, we like to combine these two methods, top-down and bottom-up, to harness the power of both techniques. For example, we can use special materials that create very small circles on a substrate, and then use top-down lithography to etch them into pyramids on the surface. These pyramids in silicon or glass have really amazing properties. They are highly anti-reflective, meaning that very little light is reflected back. They can also be what's called super hydrophobic. They do not want to get wet at all, so when water hits them, it just gets repelled very easily. As you can imagine, these properties are very useful in a lot of applications. For example, in solar cells. In a solar cell, we want as much of the light that comes in to stay in there to be turned into electricity. So an anti-reflective surface is very beneficial because not a lot of the light is reflected, it mostly goes in and is captured, and so we have a more efficient solar cell. Similarly, if it's super hydrophobic, it's going to repel things like rain and snow, as well as be able to be cleaned off with dust very, very easily. That's just one example of the many, many exciting scientific things we can do here in the nanofabrication facility. I'm looking forward to answering some of your questions.
Awesome. Thanks so much, Aaron, for that wonderful video. And it seems to be like there's a lot of interesting stuff going on with solar cells. But what I'm curious about, and I'm sure the audience is as well, is what are you exactly looking to improve about solar cell materials, and how does the nanofabrication facility help you do that?
I mean, in general, when we're talking about solar cells, we want to just make them more efficient. So there's a lot of different ways to make them more efficient. What I talked about just now in the video was making them more efficient by changing the actual physical structure of the surface so that it collects more light. More light comes in than it's reflected. So that's one way of making it more efficient. And that's done by just physically changing what the surface looks like. Instead of being flat, now it's got some topography to it, some roughness to it, and that actually makes it much more anti-reflective. And so that's one way. Another way is by changing the materials, studying the materials. Of course, we work at the Center for Functional Nanomaterials, so we want to be able to use materials that have function. In this case, the function might be turning light into electricity very efficiently. And so people might have ideas about materials, or they've actually made custom materials that don't exist anywhere, and then they want to test them, and you would test them by shining a light on them and seeing what kind of electricity you get out. And so you might want to make a little test device, something very simple, but it'll give you a lot of insight into the physics of the material. And so you might come to the nanofabrication facility to make a little prototype device and then take that somewhere to be tested. So that's a couple of examples of things in terms of solar cells. But really, whenever you're talking about changing a structure or interfacing with materials on the nanoscale in a customized way, you need to be able to make something, and that's done in the nanofabrication facility.
Awesome. And we have a follow-up question, kind of tying back to what you were just talking about. Jim on Facebook asks, what's the barrier for solar energy production being cheaper than traditional coal and oil per megawatt of power?
What was the question? I don't know if I know the answer to that.
Let me try again.
Yeah.
What's the barrier for solar energy production being cheaper than traditional coal and oil per megawatt of power?
The barrier, well, I think it's really a production thing, and that's really beyond what we do in the facility. But in terms of obviously things we do, and we want to think about materials that are cheaper, or ways of manufacturing that are cheaper. And so, one of the example we talked about where we're adding this topography to surfaces. What we do here is we kind of study the materials or the structures and the process. And then the idea is, well, what's the next step? And so that technology I talked about was actually licensed to a small company that took that and tried to turn it into something that they could do at large scales. We don't make large scale, we're a research facility, but we want to be able to facilitate moving these things on. And so that's actually another example of the kind of thing where we've coupled with industry. We're trying to take that and make it into a cost-efficient method to create structures that will have these amazing properties. Of course, we can create them in the laboratory, and the next step is let's get them out into the real world. And so that's one of the things we do, is partner with companies that are thinking about taking them. So that step is we're at the beginning of that step, but that's something we always have an eye on, or in a lot of cases we'll have an eye on.
Okay, cool. And you know what? Speaking of collaborations, a viewer on YouTube had asked, what are the opportunities or avenues for startups to collaborate with the CFN?
Yeah, it's a great question. A lot of our users are academics. They're looking at basic research, but we certainly want to be a place and are a place where small companies and large companies can come. And certainly we are in a sort of ideal situation for a lot of startups, because we have so much wonderful equipment that would be hard for a small starting company to get their hands on, and we would love to work with them. So we have, you met Priscilla already. She's really the person to get in touch with, but anyone, and you go to our website and you find a lot of places to get in touch with us. And there are actually a lot of different avenues for a company to work with us through our user process or through other avenues. And we are more than open and willing to talk and not just, I mentioned access to these equipment, but also access to the people you see here. So that's sort of the 2-for-1 deal you get when you come to the CFN. So there are a lot of opportunities. One of the people on this call is exactly the person you should talk to, is Priscilla.
Nice.
And that's an excellent point. And I guess just wanted to say to that viewer that not only can we help you access all these amazing facilities and work with the scientists, but we can also brainstorm the possibility of you working with us on a SBIR proposal to get funding from the Department of Energy or any other federal agency. So I'll also put in the chat link to the SBIR program, the DOE SBIR program. There's a call that the letters of intent are due tomorrow. So we might not be able to talk before tomorrow, but for the next time.
Perfect. So, Erin, I have one more question for you before we move on. And I apologize in advance if I mispronounce the viewer's name. Cancana on YouTube asks, and this is a little bit more technical, how do you suggest to control the contact resistance as it plays a major order determining electroconductivity/mobility?
Yeah, I mean, that's a great question. That's certainly the kind of thing that that users are always worried about. And so, CFN is a great place to study things like that, because we have the ability to sort of survey a large number of materials. So of course, what they're talking about is you have a material and you want to put a contact on there, and if you have a bad contact, you're not going to get a good conductivity of electricity. And so the things that matter, of course, is the contact, how it is made, and of course the material and the interface. And so on one hand, we're going to look at a lot of different materials. Of course, we have theorists who can help us simulate or model. And then we have a bunch of people on this, other people on this call. I'm not a microscopist, but of course we have, what we want to do is look at these materials and the interface and look at it as in as small scale as possible, on the atomic scale, and so that's what we can do, and not just look at it, but look at it while, say, we're running electricity through it and seeing how that material, how it changes. So that's what we call, in operando or in situ measurement, where we're looking at something that's going on. And so all of those phases are things that we do at the center, and that's things that we think about. What's happening in interface, how can we control it through when we're making these materials, when we're making that interface, and then what happens when we're actually running the device. So that's a great question. It's a great example of this sort of multimodal study that we can do at the CFN. And it's a challenge, of course. Whenever you come up with a new material, you got to interface with it from the outside world, and that's a challenge, and that's the kind of thing that we're very interested in studying, for sure.
Exactly. But if it wasn't a challenge, wouldn't be worth researching,
Of course, yes. There's challenges that we relish here for sure.
Exactly. All right, awesome. So I'm going to turn things over to Priscilla to kind of wrap up Aaron's segment and lead us to our next panelist.
Thank you, Aaron. Trishelle, that was great. So one of my favorite segments, I guess one of the viewers asked about why don't we use more solar cells in general? And I think one of the main problems is that our batteries are not there yet, up to par to the research in solar cells. So it's a great segue to move on to our next scientist. So our next stop today is the Scanning Transmission Electron Microscope, or STEM, with Suyan. So let's find out more about the instrument and how Suyan's research focuses on catalyst and battery materials.
Hello, I'm Suyan Huang, and I'm here at the Center for Functional Nanomaterials with Operando Scanning Transmission Electron Microscope. I'm one of the scientists who regularly uses this powerful instrument for materials science research. Let me show you how it works. This microscope works on the same basic principles as optical microscope, but uses electrons. Because wavelength of electron is much smaller than the wavelength of the light, this electron microscope can provide much higher resolution than optical microscope. It means we can resolve very tiny details in a sample, the details we wouldn't otherwise able to see. This electron microscope operates by sending electron beams to very thin sample. Electron beam is generated at the top, and electron comes down to the sample around here. And the electrons interact with the sample, and various signals are coming out from these interactions. And we record these signals to characterize various properties of the nanomaterials. Let's see how the real image looks like. The electron microscopes allows us to see very tiny details like nanostructures and even atoms in a sample. Here we have atomic image of platinum cobalt nanoparticles for catalysis. And it also allows us to see the chemical compositions in the sample. Here we have materials composed of 5 different elements, and each color represents different element. The really good thing is we can observe the sample in operando. Operando means we are looking at the materials while they are operating or working. Here I have lithium-ion battery materials, and lithium metal is at the bottom. When lithium is inserted into the materials, we can track how the structure and chemical composition changes. And these kind of studies are very useful to improve battery performances, like to make batteries that last much longer or recharge more quickly. And scientists use this electron microscope to study all kinds of the materials beyond the batteries, from catalysts and metals and to semiconductors and solar cells. I hope you enjoyed this short tour, and I look forward to talking with you soon.
Thank you, Suyan. That was great. So you mentioned that this microscope allows you to see changes in the atomic structure and chemical composition of the materials as they're working. Why is it important to capture these changes?
Well, the atomic structure and chemical compositions of materials are really important to understand the performance of the materials. For example, the cathode and anode materials for commercial lithium-ion batteries have layered structure, which has layers. So lithium ions can move easily through the gap between layers. However, if the layered structure is somewhat damaged, lithium ions have hard time to move around. That limits capacity of the battery. To make layered structure more robust. One method we can try is using different elements with controlled distribution. So understanding and the atomic structure and chemistry of materials during operation is important. And we can do this kind of research with transmission electron microscopes.
Great, thanks.
Awesome. So I have a follow-up question, Soo-Yeon. I was curious to learn more about what other types of applications you look at for batteries. We talked about solar energy and the challenges of energy storage with regards to that technology, but you mentioned lithium-ion batteries, and I know those were recently in the news a couple years ago, given some of the issues with the Samsung phones, for instance. So what work are you doing on those avenues, or what other types of applications are you looking at?
I'm also interested in catalysts, because catalysts are making energies. So batteries are just, it is like storing energies, but fuel cells or other catalysts actually can generate the energy. So I also like to explore catalyst materials too. And currently the catalysts are based on platinum-based materials. So we are trying to replace partially or entirely replace platinum with other materials like cobalt, iron, or nickel transition metals.
Cool, awesome. All righty, thanks so much, Soo-Yeon. I'm going to sound like a broken record, but just as a reminder, if you have any questions out there in virtual land for Soo-Yeon or Aaron thus far, please enter them into the chat and we'll be sure to answer them at some point during this time. With that said, we're going to move on to our next panelist, which is Greg, and we're going to be visiting the Quantum Material Press. So this is an automated platform for making materials for next generation computing. So Greg, the stage is yours.
Hi, my name is Greg Dirk, and I'm a materials scientist at the Center for Functional Nanomaterials. And what I'd like to show you today is called the new tool that I've been helping to build, called the Quantum Materials Press, or QPress. And what this does is this is a tool that's meant to automate the assembly, stacking of atomically thin two-dimensional materials into layered structures that we call heterostructures. The reason being is that these heterostructures have really astonishing quantum properties that may be used in the future for energy efficient electronics. Now the thing is, right now, a lot of scientists are working on this, but they assemble these heterostructures by first exfoliating them from bulk crystals using Scotch tape. This is by hand. Then they spend hours, days, weeks trying to find really the best kind of piece of a layer, or what we call a flake. And then they try and carefully take these flakes and stack them on top of each other. And if they get it right, then they can build a device. But there's a lot of chance for failure. So the thing is, this is ripe for something that you can automate. So really, we build this really large, incredibly complex instrument to make that automation possible. Right now, you're seeing this at an early stage, still in development. Now, it is composed of various modules that do different processes in this overall assembly process. And what you're seeing is, for example, we have a robot that will pass the wafer around to points where we will have future process steps or modules. And these will do things like exfoliate the material from the bulk crystal so you can get exactly the flakes you want. Look around using machine learning to find the best kind of flakes that you need for devices, and then precisely and quickly assemble these, eventually all without direct human input. So this is really something we believe will kind of transform the whole science of 2D material device fabrication.
Awesome. Thank you, Greg, for showing us the Quantum Material Press. It's very interesting that this is the first of its kind. And just remember, if you have any questions for Greg about the Quantum Material Press or anything else regarding his work, please enter them into the chat of your respective platform. In the meantime, we do have some questions already queued up from the audience for Greg. The first one that I have is learning more about how you actually extract out these atomically thin flakes to study from different types of materials, Greg.
That's a very good question. So, you know, in part of this research is to understand exactly how this phenomenon works, but in the simplest way, you can just take Scotch tape and kind of press it against a kind of bulk crystal that's something you could even hold in your hand, and just repeatedly press it against, you know, a sample. And over time, you'll get a distribution of flakes with all different sizes, thicknesses, and some fraction of those will be the atomically thin single layers. So you're kind of relying on some statistical randomness, but there are things about the way you do this, the mechanics of it, that actually can skew that distribution. And that's a big part of kind of the research that we're doing and that we're involved with our users who we collaborate with.
Cool. And I think Priscilla had a question to ask you as well. She mentioned to me a little bit earlier she was curious about.
Yeah, I really like this question from a viewer on YouTube. What are the most active areas of material research right now? Thin films, batteries, quantum computing, biosensors. Like Greg.
This is
bath now.
Yeah. This is a loaded question because you get 10 different answers from 10 different researchers. So I do know, you know, batteries are a huge area right now because we, you know, they're such an important for energy storage. But recently there's been a huge push for quantum computing, and, you know, you hear stuff from Google, from Microsoft, from all these major companies investing heavily in quantum computing, and it's really a prime topic for academic labs. So kind of 2D materials happen to be one platform kind of material that has drawn a lot of interest. So I think there's a lot of interest for 2D materials and for quantum computing more generally, even beyond. So that's a very hot area of research, I think, right now.
So what exactly is it about the quantum computing that's so attractive?
I think what's interesting about quantum computing is it's a fundamentally different way of doing computing than our traditional. You know, basically we use computers, and what they can do is they can do, you know, thousands of computations in a second, but they're all ones or zeros. So you have to add them all up to get something that you can use. Quantum computing can do only, like, say, one computation, but because it contains so much more information, you're actually answering something that's far more complex. And a lot of the things you're trying to answer are actually quantum questions. So what's happening inside of molecules and atoms and things like that, that's hard to understand using a traditional computation. So, but if we can understand that better using quantum computing, we can develop better materials and really accelerate research. So I think that's a big thrust for why quantum computing. It's much more efficient for that kind of calculation.
Cool. And so you mentioned using this for analyzing materials. So the two-dimensional materials that you mentioned in your video, I believe, you had also said that they may be used for the future of energy efficient electronics. Can you elaborate a little bit more on how with quantum computing?
Yeah, it's kind of related to how I answered the last question, but basically in a number of contexts you can replace traditional computers. And there's like really a great example recently from, you know, they did a study at Oak Ridge using one of the world's top supercomputers, and they compared what a quantum computer could solve that, and it would cost 1/10,000th of the energy, and the energy required is somewhere on what a typical household would use in a year. So basically you can save tens of thousands of energy if you can have a quantum computer do some of these calculations that are of high interest to science and to society. So.
Nice. So we did get an additional question in the chat. What machine learning techniques are useful for flake extraction? And what are the big challenges to overcome?
That's, full disclosure, I am not a machine learning expert. So, the thing is, this kind of project is so collaborative, and actually it's not really just quantum scientists. We have scientists, material scientists, computer scientists, everyone involved in this to try and solve these problems. So I can't answer specifically what machine learning algorithms are best. What I can say is some challenges. Oftentimes you can see these 2D flakes in a microscope, but there's a distribution of sizes, of shapes. You might have some gunk that is on there, and that's not a flake. And you can look at this in different colors and different contrast. For a human, it turns out we can get really good at distinguishing what's exactly, is this a one single atomic layer based on the contrast we see in the optical microscope. That's something that turns out is very difficult for a computer to do with the same kind of accuracy. So, but computers can learn how to do that. And so these are kind of the challenges that we're overcoming. It's kind of like a machine learning combined with machine vision. So
nice. So we do
one
have,
more.
Oh, sorry, go ahead, Priscilla.
There's a question from Rituraj on Facebook. Can you elaborate on what you mean by quantum material? He's asking us to take a little step back.
That's a good starting point.
Yeah. So quantum physics is, the kind of non-determined, physical phenomena that happen, at the atomic level. And the thing is, it's because of that, you kind of sample whole distribution. So there are these quantum phenomena that are happening, within atoms or at the atomic level. And there are materials that people have found that can allow us to control or to understand these kind of quantum phenomena, this kind of atomic scale phenomena, and to use that in place of traditional computing, where you have like kind of a switch where you just turn it on or off in traditional computing, and you just add a billion of those up. But in quantum computing, you have a kind of a sample of different, states in which an electron can be in. And so that gives you a sense of what is happening in quantum materials. We can kind of control and understand what's going on there.
So we do have time for one more question, potentially coming from a future consumer. How far away are we, Jim on Facebook asks, from a quantum desktop computer?
That's probably a far future thing, and I'm sure some people could answer that really well. I think right now we're just trying to demonstrate, at the fundamental level, can we achieve quantum computers that are stable, that can be used, continuously. So there's a lot of research, and that's kind of our bread and butter, is the fundamental research. So eventually, I think some companies will have something, but maybe not a desktop computer in my lifetime.
But if you are able to accomplish it, Greg, he will be taking pre-orders for your gaming rigs based on quantum computing. Thank you so much, Greg. We really appreciate your time.
Happy.
So we're going to move on to our last panelist for today. This is Percy, who is going to be showing off his custom-built one-of-a-kind microscope. So we're going to learn more about how this powerful instrument is used to study the structure of petroleum molecules to help develop cleaner fuels.
Yeah, hello, I'm Percy Zahl. I'm a physicist at the Center for Functional Nanomaterials, and today I'm going to show you a microscope which I've custom upgraded to image the chemical structure of a single molecule. And this microscope operates at very low temperature. That's why it's in this steel and vacuum method and at ultra high vacuum. So it's kept at 5 kelvins or minus 450 Fahrenheit. And yeah, that allows me simultaneously to image in scanning tunneling and atomic force microscopy mode for a very long time on the surface. to look at molecules undisturbed. So that's very important, as I have that clean environment. And this suggests this microscope is a scanning microscope, and it scans line by line with some fine tip over a surface and reassembles an image from that. But it uses an atomically sharp tip, and the tip end in this case can be even specifically functionalized with its carbon monocyte with a single molecule to be non-reactive, to go really close to molecules on the surface without disturbing them, without reacting with them, because only then I can image the molecules as they are. So I'm measuring the force between my tip and the molecules while scanning over them line by line, and that gets reassembled in an image. And those images, once everything is working, are kind of like magic, because they look pretty much like in a textbook, these chemical structures. You know, you see all these rings and atoms, how they're connected atom by atom. We can even identify different types of atoms or distinguish them to some degree. And those images are kind of important because if you image single molecules, only then you can also look at complex mixtures of molecules like you have in petroleum or something. If you have a mixture of things, you can't separate. All classic methods of analyzing the structure of molecules fail pretty much because you have too many and they can't distinguish. But we can look at single molecules one by one. We don't, no matter what there is, we may not be able to look at a million different molecules because we are running out of time. But we can look at single ones and get some idea of what's going on there. And that's one of the purposes these machines can be used for. Beyond many, many other physical and basic chemical properties we can analyze with this machine. And so I hope it gives you some idea what a scanning tunneling or scanning atomic force microscope is. And I open for questions later. Thank you.
All right, Percy, this is an amazing machine. And we're so happy you were able to take some time to share a little bit about it with us today. So you mentioned that the microscope enables you to study petroleum in a way that's difficult to do with other methods. Why are researchers interested in understanding more about the chemical composition of petroleum?
Well, that's a good question. What actually started the whole thing was some previous experiments were done actually at IBM and other laboratories looking at petroleum molecules and actually from various sources in different oil fields, etc. And the only method you can look at oil is on an averaging scale. You can see what kind of masses of molecules are in there with spectroscopy, but there's an abundance of arbitrary, almost it's the most complex mixture of molecules on planet, more or less, what's in oil. And it's very, very hard to get hold of what's actually in there. So, and this method, or the microscope approach, is actually able, if you extract a very few molecules, this tiny droplet, or well, kind of, and put a few on the surface, I'm actually able, and a few other laboratories as well, to look at a single molecule, not as a mixture, but you see several molecules. You can pick one and look at it in all detail and see what's in there. And that's a very unique thing, what I can do, what applies to a very wide range of chemistry also in general. But that was one very cool example, and we're able to see and distinguish where there are, for example, sulfur atoms and what kind of ring structures those molecules, complex molecules, are consisting of. And we did see the individual structure like it's pretty much drawn in a textbook that is really unique, and it enables us or the chemist to develop on future new methods to in general, simply speaking, to make fuel cleaner, maybe make a better method to get all this sulfur out of there, or the nitrogen, what creates all these NOx, what makes our air pollution even here on Long Island, what's terrible. So if we can reduce all that, that would be great. But that's a big challenge to do this in an affordable way, but efficient. And to understand that, you need very basic fundamental picture of what you really have, and only then you can tackle the problem. And that's one of the ways we can do it. Not there's a solution yet, but we get a better idea of what's in there, and we're still working on various projects as we speak, pretty much.
Awesome. And Jim on YouTube asked, and I think you alluded to this earlier from the previous question, what is the resolution of this microscope? Are we looking at order of a nanometer, since you're talking about viewing molecules?
Yeah, that's an excellent question. I'm used to say this microscope is pretty much the ultimate microscopy you can think of. because simply that I can look at dimensions of a molecule, single atoms, and how they bond together in a molecule. You see these structures like rings, different molecules, you really see those. And why I'm saying ultimate is because in real space, there is no more you can see. We can look at different properties. There is still a vast exploration like spin properties, electronics, and quantum states, and all these features. But in real space, really a picture of things. What is, we can't look smaller, because then we get in this strange world, what's called quantum world. You can't really talk about dimensions or distances anymore. That's what our big core guys in physics at RIC do. They smash atoms together, but they can't get a picture really. I mean, they get a lot of information what's in there, what the composition of a nucleus is, but there's no way anyone could draw a picture of it. It was not possible. Physically, you can't. You can stay, there's particles, there's energy, there's waves, there's all kind of forces and whatever, quarks and gluons in there, but you can't draw a picture. Bottom of that range. And with my microscope, I can look to the edge of these dimensions and there's no more to see. So if you want a length scale, that is the order of picometers of resolution. So you see two atoms bond together, you can't see any structures in between.
Percy and Kankona on YouTube asks if they have to be 2D materials for you to be able to analyze the samples, or can you extrapolate into nanoparticles, like to get Janus nanoparticles?
Yeah, that is another perfect question. Right now, this method is more or less limited to a planar molecular structure. So if I have some kind of, I call a Woolnol, a big protein, something 3D, I can't look inside. I can look eventually on top of a structure or see the 3D, how it looks on the outside, but I can't look inside. So ideally I have something flat on the surface, but I can't slice obviously a molecule up and look in it layer by layer. That is at least not yet possible, put it that way.
Lewis on Facebook asks, how do you prepare these samples in order to be viewed in the microscope?
That's another perfect question. That is actually a major part of the work. We need to start off with an extremely clean, well, perfectly clean, typically a metal surface like a copper or silver single metal crystal. So we clean this before in ultra high vacuum. That is vacuum like better than in between, like in outer space, far away. So something like 10 to the minus 10, actually my machine, if you want a number, my pressure in there, the residual gas is somewhere below 5 to the minus 11 millibars in there, what is very, very low to little to nothing. And inside the microscope, it's virtually nothing because it's in a very cold environment. It's at 5 kelvins and surrounded by 5 kelvins walls. That means if there's anything flying around that sticks to this wall, and there is virtually nothing left on my surface. So the surface stays clean once I've cleaned it. There is methods called sputtering, whatever, and it's a lot of procedures to clean the surface. That is step one. Then I have something clean, like a clean tablecloth. So now I need to put something on there, like the molecule I want to look at. There's various ways to do this. One very simple way what we're doing is called flash deposition. You put a tiny crumb of something, micrograms, whatever, just a dust on some surface, like a silicon piece of silicon on the outside in air, and I put it in my vacuum. I can heat the surface up, and then the dust pretty much flies off, so it evaporates, and I point it towards my sample in the microscope, and then if I do it right amount, I get just a very few molecules spread out on my white tablecloth, and I can eventually image them. To put it simple, that can be done in some ways. It's a job of a day or two if everything works well as a preparation, and I'll get the images. That depends on many things. It can happen within next or same day, or maybe take a week to get me something, or maybe if it doesn't work, there could be reasons that it doesn't work. I'm out of luck, but that's the time scales and the communication we're thinking about. But that's cool. Once it's working, it's kind of magic, and it's worth the trouble, put it that way. So I'm loving doing that.
So one more question for you. It seems like some of our viewers have been focusing on the aesthetics of your instrument. Ed on YouTube asks, why is there crumpled aluminum foil on the instrument? And what is it made of, aluminum or something else? And what purpose does it serve?
Yeah, that is a typical question. I hear that a lot. The aluminum foil, well, in this case, is a real, well, I use for multiple things. We need to bake this system to get the very, very high cleanness inside, and we need to cover windows with something that doesn't melt. just to insulate them thermally for radiation and shielding a little bit. That's one thing. Aluminum foil is the cheapest thing you can do for that. And another thing is I tend to cover my windows to avoid getting light in there. That is why these things are sitting on these windows there right now, blocking the light getting to my camera. Because there's light getting through a window, through a crack, to another window in my microscope. That is actually raising the temperature from 5 Kelvin to 5.1 Kelvin. That makes a difference and makes my imaging unstable, believe it or not. This is just some crumbled, because use aluminum more and more over a longer time, recycle it, get a little crumbly.
Awesome.
Thank you, Percy.
Are you working on any further upgrades to this microscope, Percy, currently or in the future?
Yeah, I mean, I'm constantly developing that machine, optimizing something on various ends. I mean, that is one side. I'm exploring new sample preparation methods, new ways to put molecules on the surface beyond the simple flash method, what I'm doing right now, actually. In the other sense, I'm a lot about instrumentation. I'm optimizing the detection, imaging, software, electronics, pretty much everything. The whole machine is home built, and there's always something new, some newer technology comes up, some new ideas, a new measurement method. You want to do it, look at different properties, you need to measurement, tune them in a different way. So there's always something new coming on. So that is a cool thing. It's continuously evolving.
Awesome. Well, thank you so much, Percy, for your time. And thank you to all of our panelists that joined us today and sharing some of their research ventures with us. We wanted to take this time to ask a couple follow-up questions to the group. The first one for each of the panelists is, how did you come to work in nanoscience? So I guess we could go down the line, starting with Aaron, make our way in the same order as our speakers presented today.
Sure. Yeah. How did I end up working in nanoscience is a good question. I don't know. I don't think anyone grows up thinking they're going to go into nanoscience. In fact, for a long time, I didn't know such a thing existed. But when I was in graduate school, as I mentioned, at Stony Brook, I was involved in a research group who actually worked at Brookhaven doing X-ray science. And without going into a long explanation, creating optics for X-ray science was very challenging, and it's something you use nanofabrication for. So I ended up developing the skills of nanofabrication for one very specific application. And over the years, particularly when I've come to the CFN, I've used that to solve all sorts of different, much different, a very wider range of nanoscience challenges. So I came across it a little accidentally and very incrementally, sort of one interesting topic at a time. And so over the years I've worked there, I've been involved in a really broad range of topics.
Nice. So Yoon, same question for you.
So in my case, I was fascinated by a picture from electron microscope, which shows an atomic arrangements. I forgot which material it was, but I was shocked to see an image from real atom. So I started to be interested in electron microscope and nanoscience. That's how I started to be interested in nanoscience. And after during my undergraduate, I picked material science as my major, and I keep developing my career in this way. I feel very lucky to see those fascinating images every day.
Thank you, Soyeon. Greg?
Yeah, so I started in undergrad. I was fascinated with the Moore's law and the idea that you could keep shrinking the transistors and put billions of devices on something that's like a centimeter squared. So I went to grad school, was introduced to nanoscience. And I think also, I did a postdoc at IBM working with polymers that self-organize to create nanoscale patterns, the idea to try to make computer chips. And this has been the kind of, to me, it just, that was like the most fascinating thing I could imagine. And so I've just kept on looking at how we can influence things to self-organize at the nanoscale with the ways. So that's been the most fun aspect, and it keeps me going for all this.
And finally, Percy.
Yeah, well, I mean, I studied physics long ago. I was always fascinated by nature and science and figuring things out, exploring something new. And it happened at one of my physical, some seminars or classes, talking to people in the lab. And I ran into something that was sitting some some machine on the table, what looked kind of interesting to me, and no clue what it is, and ended up being scanning probe microscope or STM at that time. And well, I kind of found it interesting, and before even doing my diploma series, I kind of got involved into it, and somehow that stuck, and it fits very well. I like these things. I like developing things from software, hardware, machinery, instruments, combining my skills. I've always loved that. I can do a lot of things in computer and programming. That's cool, but I never want to do this for a main job, you understand? But I like to deploy my expertise for some problems, so something in physics. So that's all that I love to do. And be versatile, have many things and many problems to work on. And right now, while looking at atoms or molecules and get these images, it's a little bit like magic. It's a lot of work, but it's also very rewarding, and I kind of love it. And I love to work with people and bring them this method to them and allow them to image something what they couldn't do in their own lab. And there's just very few people to have the material, the expertise, and the machines to do that. So yeah, I'm more than happy with that.
Cool. Well, thank you so much, everyone. Priscilla, did you have any additional follow-up questions for our panelists, or did you want to talk a little bit more about the outreach activities you had mentioned throughout the live stream?
Yes, thanks, Michelle. So I put on the chat, the YouTube chat, the link to Nano Day, so October 9th, and for the SBIR program for small businesses and startups. And, if you like to talk to us about your future plans or proposals, we'd be more than happy to engage and see how we can help, and hopefully help you prepare a better, stronger proposal. That's always exciting for us too. And we have a great team, so hopefully you can reach out.
Awesome. Well, if we don't have any other questions, we can go ahead and wrap up this year's CFN Summer Sunday. So I want to thank everyone for joining us, our panelists, our viewers. I hope that you took away from this experience learning a little bit more about our facility and the current science that we're doing, and continue us to follow us online and learn more about what's going on with these researchers and other members of our team.
Thank you. So I guess this concludes this year's Summer Sunday series. Stay safe and keep in touch. We hope to see you in person next year. Thank you, everyone.
Bye-bye.